Our next problem is also very interesting combination of a circle and a hyperbola. We have a variable chord of the hyperbola which is touching the circle, that is, it is acting as a tangent to the circle. We need to find the locus of midpoint of all such chords. Now, as we did earlier, when a line acts in two different ways for two different curves, for example, in this case, a line is acting as a chord for the hyperbola and it is acting as a tangent to the hyperbola. What we can do is, we can write the equation of chord for the hyperbola, and since it is a tangent to the circle, we can drop a perpendicular from the center to this chord and equate it to the radius r. Or what we can do is, we can write the equation of this variable chord having a middle point h comma k. In the similar fashion, we can write the equation of tangent for this circle and we can compare both the equations. Since the same line is acting in two different ways for the circle and the hyperbola, we'll try to solve the problem in both the ways. Now, if h comma k is the middle point, then a line whose middle point is given by t is equal to s1, as we did earlier. So it is xh upon a square minus yk upon b square is equal to 1 is equal to, h square by a square minus k square by b square. This is the equation of the chord whose middle point is h comma k. Now the line which is acting as tangent to this circle can be given by x1 plus y1 is equal to c square. This is a general trick, or rather a very important formula that can be remembered in this way, that for any curve, let's say the circle in this case, the equation of a tangent at any point x1 comma y1 can be directly written by replacing one of the x by the point x1, one of the y by the point y1 in that equation of the curve to get x1 plus y1 is equal to c square. Let us take any general point x1 comma y1 to be equal to c cos theta comma c sin theta in our case. Hence, the equation of tangent becomes x cos theta plus y sin theta is equal to c. Now, since both are the equations of same line, we can compare the coefficients of x, y and the constant terms to have h upon a square cos theta is equal to minus k upon b square sin theta is equal to h square by a square minus k square by b square upon c. The value of cos theta comes out to be equal to hc upon a square times h square by a square minus k square by b square. The value of sin theta comes out to be equal to minus kc by b square times this term again h square by a square minus k square by b square. Now we can do cos square theta plus sin square theta is equal to 1, which gives h square c square by a power 4 plus k square c square by a power 4 is equal to h square by a square minus k square by b square whole square. Now h can be replaced by x and k by y to get the locus as c times x square by a power 4 plus k square plus y square upon b power 4 is equal to x square by a square minus y square by b square whole square. This was our first method in which we compared the equation of the line acting as a chord with a given middle point to the hyperbola and as a tangent to the circle. In our second method, what we can do is, this chord acting as tangent to the circle, we can draw a perpendicular from the center 0, 0 and equate it to the distance r radius. So it is equal to h square by a square minus k square by b square upon under root of h square upon a power 4 plus k square upon b power 4 is equal to radius, which is c in our case. We can very clearly see that on squaring both the sides, we get the same equation, that is x square by a power 4 plus y square by b power 4 into c square is equal to x square by a square minus y square by b square whole square, which is our locus of the midpoint of all such chords, and this is our final answer.